All right, so you sent over this paper about superposition in neural networks.
Yeah.
Toy models of superposition.
Yeah.
I mean, I don't know about you, but when I first saw the title, I thought, well, this will be pretty straightforward.
Yeah.
But I was reading through it, and it's actually, it's got some pretty profound stuff in there
Yeah, it's quite deep, actually.
about how we understand and also build neural networks.
Yeah, definitely. It gets into how neural networks actually represent the information.
Yeah.
And it uses simplified models to give a really clear view.
Right, these toy models.
Yeah.
But the findings themselves are anything but toy-like.
Right, exactly.
And what really struck me was this idea that networks can represent more features than they have dimensions.
Yeah.
How is that even possible? That's like fitting, I don't know, like 10 pounds of flour into a 5-pound bag or something.
Yeah, I mean, imagine you have a point in like a 2D space.
Okay.
You can define it with 2 coordinates, right?
Right.
But what if you need to represent 10 points in that same space?
Yep.
Superposition is kind of like saying, okay, let's blend these points together in a way that we can still decode later.
Okay.
It's not about cramming more information into the same number of dimensions, but rather using those dimensions to represent combinations of features.
I see. So it's more like I don't know, a carefully choreographed dance or something rather than just like a chaotic free-for-all.
Exactly.
Okay.
And the way it works is by introducing nonlinearity through activation functions, like
Right.
ReLOU, for example.
Okay.
They provide the flexibility to create these complex combinations.
So the paper uses these toy models to demonstrate this.
Yeah, exactly.
Like they show that a ReLU network can represent, say, 20 features in just 5 dimensions.
Right.
Whereas like a linear model is limited to 5.
Yeah, stuff.
That's a big difference.
Huge difference.
So it seems like this nonlinearity is kind of the key
Yeah, absolutely.
that unlocks this power.
Yeah.
And I think it's interesting because we often think about activation functions,
Yeah.
like in terms of learning and computation.
Right.
But this research highlights their role in shaping the representation of information in the first place.
Absolutely. Yeah. Reframes our thinking about the building blocks of neural networks.
Yeah.
It's not just neurons firing or not.
Yeah.
It's this intricate interplay between the features within a single neuron,
Oh my.
a single neuron's representation.
So this interplay then leads to some really unexpected results.
Yeah.
For me, at least,
Mhm.
when I got to the part about the geometric patterns
Yeah.
that emerge,
Yeah. It's remarkable.
triangles, pentagons.
Tetrahedrons.
Yeah, it's like neural networks are secretly obsessed with geometry.
Yeah. Who would have thought?
It's crazy. And the fact that these patterns correspond to solutions to the Thomson problem,
Yeah.
which I had to, go and refresh my memory on what that was.
Right.
But this classic physics problem about the lowest energy configuration of electrons on a sphere.
Yeah.
Like that connection suggests there's something deeper going on between neural networks and fundamental principles of physics.
Yeah.
It's not just random. There's some structure to it.
Elegance.
Elegance.
To how they arrange themselves.
Okay, but let's get down to like the practical implications.
Yeah.
Because you're out there in the trenches
Yeah.
building these models,
Let
right?
me try to.
Deploying them.
Yeah.
So how does this idea of superposition, how does it change your approach?
It's definitely been a bit of a blind spot, I think.
Okay.
We focus so much on performance, like getting the accuracy higher and higher,
Right.
that we don't fully think about what's going on in the black box.
So this research is kind of like a wake-up call then.
I think it is.
Okay.
Yeah, it's forcing us to think about whether we actually fully understand how our models are making decisions,
Right.
especially with superposition.
Yeah.
Like, take interpretability, for example.
Okay.
If features are all mixed up
Right.
because of superposition, how do we know what each neuron is actually representing?
Yeah, you can't just say that neuron is a fluffy detector
Right.
because it could be representing all sorts of things.
A blend of things.
Yeah.
Some of them might be totally unrelated.
Right. So it's more than just finding the right labels for the neurons.
Yeah,
It's like they have multiple meanings, potentially.
exactly. Multiple or even conflicting meanings.
Right. And this then ties into this whole issue of adversarial examples.
Yeah.
Right. So the paper found that models with higher levels of superposition are more vulnerable to these
Yeah.
carefully crafted inputs designed to fool the network.
Absolutely.
It's like the more you pack in,
Yeah,
the more potential points of failure there are.
exactly.
So if a neuron is responsible for all these different things,
Yeah.
it's easier for an adversary to exploit that.
To exploit those ambiguities. Yeah.
And trigger the wrong response.
Exactly.
So then it makes you wonder if superposition is inherently a problem
Yeah.
for tasks that require robustness and reliability.
That's the question.
So what do we do about it?
That's the big question.
Is there any way to reduce the negative effects
Right.
without losing the benefits?
Yeah, so the paper explores 3 main strategies.
Okay.
The first one is to train models that exhibit less superposition
Okay.
in the first place.
From the get-go.
Yeah, they suggest things like L1 regularization,
Right.
which penalizes the network for using too many features per neuron.
So it's encouraging it to be more organized.
More organized, yeah.
But wouldn't that then limit its ability to learn complex relationships?
It's a trade-off,
Right.
for sure.
Okay.
And for some tasks, you might not be able to eliminate superposition completely without sacrificing performance.
Right.
So that's where the second strategy comes in.
Okay.
Finding an over-complete basis
Okay.
that allows us to decode the superposition after the network's been trained.
So instead of preventing it, we try to unblend it.
Exactly, yeah.
Yeah.
Techniques like sparse coding
Uh-huh.
and dictionary learning
Okay.
might be helpful here.
So we're trying to identify.
A set of virtual neurons
Right.
that represent the original features.
Even though they don't correspond to the actual neuron.
So the physical neurons, yeah.
This sounds really computationally challenging,
It is.
especially for large models.
Yeah, and it also creates this additional layer of abstraction.
Right. So it becomes harder to understand what's going on.
Harder to grasp how the network's actually doing its computations.
Okay. So we gain interpretability, but then we lose transparency.
In a way, yeah.
What about hybrid approaches?
Yeah, so that's the third one.
Okay.
Maybe we can reduce superposition during training
Rebecca.
without sacrificing too much performance
Right.
and then use decoding techniques afterwards.
It's about finding the right balance.
Exactly.
Okay. Now, this has all been focused on models without a privileged basis.
Right.
So what happens when we introduce one?
Yeah, that's where it gets really interesting.
Okay.
So the paper looks at a toy model that computes the absolute value function.
Okay.
Simple function.
Yeah.
But it needs to use RILU.
Which creates this nonlinearity
Okay.
and the privileged basis from those neurons.
So the RILU is not just a theoretical tool here.
Right.
It's part of the computation.
It's integral.
Okay, so what did they observe when they trained this model?
So when the input features are dense,
Okay.
it behaves as you would expect.
Okay.
Each neuron represents a single feature.
Mm-hmm.
Nice and interpretable, monosemantic.
Right.
But when you increase the sparsity of the input,
Okay.
things start to shift.
So it starts to exhibit superposition,
Exactly.
and now it has to do it within these constraints.
Exactly, with the constraints of the privileged basis.
Okay.
And what happens is that the features start grouping together
Okay.
on specific sets of neurons.
So it's trying to maintain order,
And maintain some order here.
even though it has to blend the features.
Right.
It's fascinating how it does that. It's like
Yeah.
it's saying, okay, I have to play by these rules,
Yeah.
but I'm going to do it elegantly.
In the most elegant way possible.
No. And it's not just aesthetics. It has implications for interpretation.
Right.
Like the paper found that neurons representing the most important features,
Okay.
they tend to remain monosemantic,
Okay.
while the less important features get mixed together.
So it's like prioritizing.
Yeah.
Prioritizing, making sure the crucial stuff has its own representation.
Exactly.
Even if the less important stuff has to be,
Compromise.
compromised.
Yeah.
That's a really good way to put it. And this aligns with what we've seen in language models.
Yeah.
Where neurons for common words are easier to interpret,
Exactly.
but the rarer ones are more polysemantic.
Yeah.
So even though this is a simplified model, it's giving us insight
Yeah, real insight.
into more complex ones.
Absolutely.
What blows my mind, though,
Yeah.
is that it can perform computations while in superposition.
Yeah. How is that even possible?
With everything all jumbled up,
Right.
you would think it would just be a mess.
A chaotic mess.
Yeah, but the paper describes this mechanism.
Yeah, the asymmetric superposition motif.
Right.
It's a way for the network to store features with different weight magnitudes on a neuron
Okay.
and then use reciprocal weights on the output side.
So it's like creating a hierarchy within the superposition.
Exactly.
Like this feature is the dominant one,
Yeah.
and the others are more like background noise.
Yeah, like murmurs.
Big murmurs.
And to prevent those murmurs from interfering too much,
Okay.
the network uses another neuron to inhibit the dominant feature when it's not present.
Wow.
So it compensates for the potential chaos.
It's amazing how it can do that.
Yeah, it's remarkable.
Perform these meaningful calculations.
It really is.
It's like, I don't know, a chef juggling all these different dishes at once
right.
and keeping all the flavors separate.
Exactly.
So this brings us to an important point, right?
Yeah.
If this is so prevalent
Yeah.
and networks can compute effectively while doing this,
Right.
how do we make sure they're not doing things we don't want them to do?
Right. How do we ensure safety and alignment.
Yeah, it's kind of unsettling, right?
It is a little bit.
Like we've created these tools,
yeah.
but we don't fully understand how they work.
And we don't fully understand the language they speak.
Yeah, right. And we're giving them these really important tasks.
Yeah.
So the authors of the paper argue that being able to fully understand and solve superposition
Yeah.
would be a huge step
A monumental step.
towards safe and reliable AI.
Yeah. Safer and more reliable AI systems.
So we need to crack this code,
Yeah.
figure out what each feature represents.
Exactly.
That sounds like a huge challenge.
It is.
They outline 3 potential approaches.
Right.
So create models without superposition,
Yeah.
find an overcomplete basis,
Uh-huh.
or use a hybrid approach.
Hybrid approach.
So let's dive into each of those.
Okay.
Starting with, creating models without it.
Right.
Is that even feasible?
Well, they show it's possible
Go ahead.
to reduce it using techniques like L1 regularization,
Right.
but it often comes at a cost to performance.
Right. So there's that trade-off again.
Classic trade-off
Right.
between interpretability, robustness, and performance.
Yeah.
Exactly.
And for things like natural language processing,
Right.
it's hard to know how much we'd have to give up
Yeah, how much performance you would have to sacrifice.
to eliminate it completely.
Right.
So what about finding an overcomplete basis then?
So that would involve developing techniques to disentangle the features
Okay.
after training
Let's-
methods like sparse coding or dictionary learning
Right.
to find a set of virtual neurons
Okay.
that represent the original features.
Even though they don't correspond to the actual neurons.
Exactly.
Like we were talking about before.
Yeah.
It's like we're building a decoder ring
Decodering, yeah.
for this language of superposition.
It is, yeah.
This is also computationally expensive,
Very much so.
especially for large models.
Yeah. And it creates a gap between the structure and the features.
Right, so it becomes harder to understand how it's working.
Right, exactly.
So again, we gain interpretability,
Yeah.
but we lose transparency.
We lose some transparency.
Okay, so what about the hybrid approaches then?
So maybe we can find ways to minimize it during training
Uh-huh.
without sacrificing too much performance,
Right.
and then use decoding techniques afterwards.
So it's like finding a middle ground.
A middle ground, yeah.
Okay.
Exactly.
This feels like something that requires a massive collaborative effort.
It does.
We need people from all these different areas working together
Yeah, absolutely.
to solve this.
Yeah.
So understanding superposition is a fundamental problem
Yeah.
for the entire AI community.
For sure.
This has really changed my perspective.
Yeah.
It's not just about building models that work.
Right.
It's about building models that we can understand
And trust.
and trust, yeah.
Yeah.
And that means dealing with these complex phenomena,
Absolutely.
like superposition.
Yeah.
But what I find really exciting, though, is that we're only beginning.
We're just scratching the surface.
Right.
There's so much we don't know
Yeah.
about how it emerges, how it varies across different types of networks,
Right.
and the best ways to address it.
So much more to explore.
Absolutely.
All right, well, we've covered a lot today.
Yeah, a lot of ground.
I think we need to take a breather.
Little breather.
But don't go anywhere,
Stay tuned.
because in the next part, we're going to dive into some specific cases
Yeah, some specific examples.
that highlight these nuances
Exactly.
of superposition.
Looking forward to it.
Me too.
Okay.
All right.
See you then.
See ya. Okay, so let's get into some of those nuances.
Yeah.
I remember the paper talked about how correlated features,
Yeah.
so features that often appear together in the data,
right.
behave differently
They do.
in superposition
Yeah.
than independent features.
Yeah.
I mean, it seems intuitive
Yeah.
that they would,
Right.
but how does that actually play out?
It's like the network recognizes those relationships and
Ah,
tries to represent them in a way that minimizes interference.
okay.
So the research found that correlated features actually prefer to be orthogonal
Okay.
to each other in superposition.
Okay.
They occupy different, what they call Tigum factors,
Tigum factors. Okay.
which are like distinct subspaces within the overall representation.
So they get their own little corner.
It's like giving them their own little corner of the playground.
Right. So they're not stepping on each other's toes.
Exactly.
Okay. So even though they're being represented in superposition,
Yeah.
they're still kept separate.
They maintain a degree of separation, yeah.
What about anti-correlated features then?
Yeah, so those are features that tend to repel each other.
Right. They don't like to be together.
Exactly.
So do they get their own separate spaces too?
Actually, it's the opposite.
Oh, really?
Yeah, anti-correlated features actually prefer to be in the same Tigum factor
Huh.
when superposition is necessary. And they exhibit negative interference,
Okay.
ideally being antipodal to each other.
So they want to be as far away from each other as possible.
Within that same space,
Yeah.
and still in the same
Yeah, it's like they enjoy being at odds with each other,
Right, even when they're forced to share.
even when they have to be together.
So it's interesting how the network seems to mirror
Yeah.
the relationships between the features
It does. It's remarkable.
in the way that it represents them.
It reflects the structure of the data.
It's not just stuffing them in there.
Exactly.
It's doing it in a way that makes sense
in a structured way.
based on their relationships.
Absolute.
So this has implications then
Yeah.
for how we interpret what's going on.
Big implications.
Right, like if we see a neuron
Yeah.
that seems to be responding to
Yeah.
a bunch of random features,
A random collection of features.
it might actually be because those features are correlated.
Or
They're
anti-correlated.
anti-correlated, right?
So it's not that the network is confused.
Right.
It's actually reflecting those relationships.
Maybe it's smarter than we think.
Yeah, and we haven't figured that out yet.
We just haven't identified those relationships.
So we need to be more nuanced
Absolutely.
in how we approach interpretability.
More sophisticated.
Yeah, we can't just look at individual neurons
No,
or
this-
features in isolation.
We need to look at the interplay.
Right, we need to understand the whole system.
The whole ecosystem.
Yeah, it's like an ecosystem.
Exactly.
This has really been an eye-opener.
It's amazing, isn't it?
Yeah, I mean, we've built these powerful models,
Incredible models.
but there's still so much we don't understand.
So much we don't know.
It's humbling,
It is.
but also exciting.
Absolutely.
It's like we're on the edge of something new.
a new frontier.
Yeah,
It's an exciting time.
I completely agree.
Yeah.
All right, well, we've covered a lot of ground again
We have.
in this part.
Yeah.
So let's take another break.
A little breather.
But stick around.
Don't go anywhere.
Because in the next part,
Yeah.
we're going to talk about what we can actually do.
Right. The strategies to address superposition.
Yeah.
Looking forward to it.
Me too.
All right.
Okay, see ya. So let's talk about what we can actually do about all of this.
Yeah, the strategies for addressing superposition.
Right, because it seems like we can't just ignore it.
Definitely not. It's too important.
So the paper outlined 3 approaches, right?
Yeah. Creating models without superposition, finding an overcomplete basis, or using a hybrid approach.
Okay, let's start with the first one.
All right. Creating models without superposition.
Is that even possible?
Well, the paper showed that it is possible to reduce it
Okay.
using techniques like L1 regularization,
Right, we talked about that.
but it often comes with a performance hit.
Right, so you might have to sacrifice some accuracy.
Exactly, it's a trade-off.
Okay, so maybe that's not always the best option.
It depends on the task.
Right, what about finding an overcomplete basis then?
That's about developing techniques to disentangle the mixed features
Okay.
after the network is trained.
So we're not preventing superposition, we're just trying to decode it.
Precisely.
Right, how would we even do that?
It could involve using methods like sparse coding or dictionary learning to find a set of virtual neurons
Right, we touched on that before.
that represent the original features.
Even though they don't correspond to the actual physical neurons.
Exactly.
But this sounds pretty computationally intensive.
It can be, especially with larger models.
And it also creates another layer of abstraction, right?
It does.
Making it even harder to understand what's really going on.
Exactly. You gain interpretability but lose transparency.
Okay, so maybe there's a middle ground with those hybrid approaches,
Yeah, that's the third option.
right? Combining the best of both worlds.
Exactly. So maybe you could minimize superposition during training
Okay,
without losing too much performance,
right.
and then use decoding techniques afterwards for any remaining superposition.
So it's like finding the right balance.
Exactly. Finding that sweet spot.
This whole conversation has really made me think about the future of AI.
Yeah, it's a fascinating time.
We're creating these incredibly powerful systems,
more powerful every day.
but we still have so much to learn
We're just scratching the surface.
about how they work, how they make decisions.
Absolutely.
And I think understanding superposition is a crucial part of that.
It's fundamental.
Because if we want to build AI that we can trust,
Yeah, AI that's safe, reliable, and aligned with our goals.
we need to be able to understand what's going on inside.
We can't treat them as black boxes.
Right. We need to shed light on these inner workings.
Exactly. And that's what this research is all about.
It's a call to action for the entire AI community.
To dive deeper, ask tough questions, and work together to solve these challenges.
And to you, our listener, thank you for joining us on this deep dive.
It's been a pleasure exploring these ideas with you.
We encourage you to keep learning, keep questioning, and keep pushing the boundaries of what's possible in AI.
Who knows what incredible discoveries await us?
Until next time, keep exploring.